Hey, okay, so it's week 2, and I'm in the Energy Y 242 Moodle shell, and I just wanted to go over a few things with you here. So I've just been using the August 2013 syllabus. Last fall, 2015, we did not teach this course, and in 2014, it was kind of a strange fall because we spent most of the time taking down the wind turbine from Hellgate Canyon. This fall, one of our projects is going to be to work towards installing the 10 kilowatt Berge wind turbine that used to sit there in Hellgate Canyon. We're going to install it at the Kettle House 3 site up the Blackfoot River. So I'm just sticking with that 2013 syllabus. So take a look, if you will, the Piggott text. This is the sort of the low-tech wind turbine text, if you will, and here's JA. That's sort of the high-tech wind turbine text. So a little more math, some more equations. The first 3 chapters are there for you, so go ahead and buy those books. If not, I've got some of the relevant material there for you. Project discussion. I'm just going to get right into that. So what I've got is I'm going to need you to have some kind of mechanical drawing or component, some kind of physics-based model or theory. And again, these projects for solar, thermal, and wind, they can be either a solar thermal project, so you're using the sun's energy to heat either water or air or perhaps some other fluid if you want to get creative, or you're going to build a wind turbine prototype. And we've got a 3D printer. I've got a wind turbine sitting in the back of the classroom right now. In fact, I've got 2 of them. So we've got all kinds of good prototypes. If you want to start working with that, so you've got a head start on that as well. Some type of physical prototype, and then some data once you've finished that. And if you've taken the practicum already, most of you have, you know what that's all about in terms of like getting some data from your system and presenting it. And then you'll have a report that shows how your physical system compares with the theory you came up with, and then final presentation. So I'm going to just add one right now and say, let's hear some ideas. Send that out. Submit that. Okay. Launch that little discussion.
So what is the Maglev wind turbine?
Oh, okay. So the question now is what is the Maglev wind turbine? And this is an idea. It's a currently patented turbine. I'm not going to go out and dig through it, but if you can imagine, it's not that hard to imagine. Everyone's played with magnets before, but if you have a pair of magnets, this is just a side view, and you've got a magnet with a north side and a south side. And if you take another magnet with a north side and a south side, you'll notice that these magnets repel each other. And so in a system like this, you have the force, the weight equals the mass times the gravity. And if the magnetic field strength is greater than the mass times the gravity, then it floats. Now, in this configuration, it's not stable, so if I were to push this, it would just simply fall off under the weight. But if you had a rotary system, some type of centralized shaft, and then you could imagine a wind turbine sitting on top, and the particular inventor has invented a wind turbine. Let's just say.
So he's basically harnessed the flux in there and sandwiched it down with something holding the magnets together.
Well, gravity takes care of the sandwiching. So it's just, gravity is pushing them together, but the magnetic field is repelling them. So when those two forces are in equilibrium, you've just got an air gap. And I'm just going to take a few shots. The particular design that this inventor has come up with, it's a lot like this guy right here. So you've just got multiple blades, and it's more or less a lift-based system. So that's all it is, maglev. And obviously when the wind blows from this direction, some of that energy is turned into spinning, which is what you want, but some of it also is turned into a bending. And if you have a shaft with you're going to have some kind of bearing up here, some kind of bearing at the bottom. These bearings are going to have to withstand the shear loads. This is the force of the wind. If you didn't have bearings on the top of the bottom, it would blow over. But the point is, the wind turbine itself is not sitting down. There's relatively little. I'll just say, the force of friction in the z direction or the vertical direction is approximately zero. That's the whole point. The whole point is to have something that's relatively low friction so that the start-in speed is modest. And that's not 100% a function of the friction. It's also a function of the EMF of the generator. Every generator takes some energy to get going. So anyway, but that's the basic principle behind it. And
So I guess the upper magnet that you got there?
Yep.
Is that floating over the bottom magnet?
Yes, the upper magnet is floating over the bottom magnet.
And the upper magnet's spinning?
The upper magnet is spinning and the lower magnet is stationary. Yeah. And and you could just imagine a couple toroidal magnets like that, and that's what the fields look like. The fields actually look like this, right? The field lines in a magnetic field are always this toroidal shape, but at the surface, the direction of the field is perpendicular to the surface of the magnet. So yeah, so that's that. Okay, super. And it's like it's not. I mean, sure, it's great. It's not like this individual invented magnetic levitation. I mean, the first time somebody put two magnets together, I mean, it was discovered, but it's just like, okay, let's put them together and get the thing spinning. So anyway, that's the project. And relatively low energy. We've got a we've got a turbine sitting right here in this classroom that we built a few years ago that, and the students wound their own generator and, worked, hooked it to a hot air balloon. It worked great. It was fun. And what else? Let's just get back into the.
Looks to me like the two magnets there are redundant, but that's just.
No, the magnets are not redundant.
The two magnets where they're setting are redundant, if you went back to the picture.
This one and this one?
Well, if you eliminated the bottom magnet and put all the bottom magnet up in the bottom of your spinning carousel there.
Oh, yeah, no, I guess, what I should have shown is that the, this is actually rigidly attached here. This whole thing spins. And the shaft is going to extend, all the way down onto some base. And yeah, this entire thing is spinning. The entire upper magnet does indeed have to spin. So this is stationary. This is spinning. Spinning. Yeah. And then, yeah, so this is week 2. I'll just show you a little bit. I'm just going to walk you through these 2 lectures. One's on solar theory. And, this first little number here is just telling you that the rate at which the sun is shining on planet Earth, the amount of energy hitting the Earth from the sun is 10,000 times greater than what we currently use. That 10,000 to 1 ratio is just telling you that humanity runs at about 16 terawatts, and the sun, this is humanity, and the sun is running at 16, 0, that would be 1,000 times. It's a 10,000 to 1 ratio. So there's approximately 160,000 terawatts of sunlight incident upon the Earth. So the point is there's no shortage of solar energy. This is some nomenclature from your textbook, your Earth scan. 1,367 watts per square meter is what's incident upon the Earth. G is the term for irradiance, and what I've got here is G sub G equals G direct, so the direct irradiance plus the diffuse. So in any solar gain, you might have sunlight coming in directly, and you might have diffuse sunlight, which might get you over that 1367. The number phi stands for irradiated power, and that's just in watts. So you can think of irradiance as sort of power flux, if you will. Phi is just power, W, watts. Q is heat quantity, and that's energy. So you're gonna integrate your irradiated power over time to get your heat quantity. So Q equals, what's that?
In coulombs? Heat quantity in coulombs?
Heat quantity is not measured in coulombs. I think coulombs is measured in electric charge. Heat quantity is going to be measured in BTUs, kilowatt hours, megajoules, etc. And so the way to think about that, is that Q equals the integral of phi over time, or in other words, the change in heat of some system equals the power times the change in time. So, for example, if we had a power coming in of 100 watts, and it was coming in for 1 hour, the change in heat is going to equal 1 1,000 watt hours equals 1 kilowatt hour. And then you can change that into BTUs, et cetera. So nothing too crazy or new on that. So that's your solar thermal. Here's what we're also looking at for energy times area times time. London on June 21st, so that's the summer solstice, is getting 8.0 kilowatt hours per square meter per day. September 21st on the equinox, it's less than half of that. December 21st on the winter solstice, it's even less. This little note over here, I'm just showing that at 0 degrees, the cosine equals 1 and the sine equals 0. At 90 degrees, the cosine equals 0, the sine equals 1. At 180 degrees, the cosine equals -1, the sine equals 0. And at 270 degrees, the cosine equals 0 and the sine equals -1. And here I've just got the angles, elevation angles. So in the morning and evening, your sun is coming in at 14.1. Later in the day, it might be much higher. So what we're looking at here is the value. So so 1 over the sine of this gamma. Yeah, let me think about that. I can't remember what AM is. 1 second. So what the area, this is just showing that 1 over the sine of 90. So the sine of 90 is 1, and if your panel, your technology is pointing directly at that at the sun, you're getting all of it. Once you fall off from that, it falls off by 1 over the sine of whatever angle is. That's just what it's showing. We can go over that when we've got more people here in class. Spherical coordinates. This is showing that if you've got the sun coming in, you can for spherical coordinates, just imagine you're on a certain latitude and longitude. So psi, theta, and z are the 3 different ways to measure that. And it is a challenge to draw. But what we're looking at here is that as we go through the seasons, as we go through the seasons and the time of day, both angles are being affected, both the elevation angle as well as the azimuth angle. And so those are the two separate angles that are there. Okay, next. Oh, and then Bett's law. Take a look at Jaw. The first 3 chapters are there. He talks a little bit about the federal wind energy program. Talks about how Denmark gets as much as 40% of their electricity from wind. The horizontal axis wind turbine are the types you typically see out on the High Line in Shelby. The vertical axis is the type we just showed. The vertical axis is either a Savonius or a Darius, and I believe that's a quiz question too. So look those up in your text. And then finally, the Betz limit. That's just a 1D approximation of the maximum amount of energy that you can get from the wind. These are the 2 numbers that are coming out of Chapter 1 on the amount derived from wind and solar. Those are going to change. So take a look, do a little bit of research on that, because the book is a little bit dated. But this is your chance to kind of see how wind and solar are becoming more prevalent in the U.S. And then I am not going to beleaguer this. I've done so in previous courses. So, and I've got my electric car guy here, but again, we'll go over the bets limit. The bottom line, really the only thing you need to know on that is once all the pieces are in place, the maximum power is 16/27, and as it turns out, 16/27 is about 57%. And what it's also telling you is that some wind has to come out the backside of the turbine, and when it does, it's typically slower. So anyway, that is the launch for 242. I will see everybody in a week. We'll talk projects, we'll talk a little more theory, and then I can't wait to get out in the field and see what you guys are going to be building this fall. So see you soon.